Welcome to Calculus and Vectors exam review for Unit 6, which was on related rates. If you remember, related rates are a bunch of different kinds of questions that we did sort of basic ones that were just volume and surface area, that sort of thing. Started with those. We had Pythagorean theorem questions. We had similar triangle questions. Substitution was another strategy. It's kind of a type of question. It's kind of a strategy. We looked at that, and we looked at trigonometry. And each one has their own unique parts that you need to be aware of, and their own style and their own things that you're looking for and how you're setting them up. So we're going to do a couple of examples to highlight some of these things and some of the general ideas. We're not going to do one of each, but we're going to do a couple. I would encourage you to go back and take a look at the advice that we talked about when we first started this, and review the things that you want to look for. I'm going to highlight a couple of them here. Generally speaking, we are comparing things to time, so we're taking the derivative with respect to time. That's obviously not always true, but for us, that was primarily what we were doing. So you want to identify and any variables that you're talking about. You may have to define some variables, or you may define them with either a let statement or just with a diagram. You are obviously going to have to write out some formulas, and you may have more than one in some cases. You certainly have to identify your givens, and that's important because some of your givens are going to be changing, and so that's after you've taken the derivative. So that's going to be very important. You want to think about what you are solving for and make sure that the formula that you come up with is going to work for that. And at some point you want to take the derivative of something, and then you're going to end up solving for what you're trying to find. Okay, so those are some general tips, advice, things to think about. Thinking about units as you're going, and how those units, kilometers per hour is a change in position over time. So that might be ds by dt, those kinds of things that you're thinking about. Okay, so let's take a look at the first one. Sand is pouring into a cone-shaped container at a rate of 2 centimeters cubed per second. Well, sand pouring into a cone-shaped container, first of all, I'm going to go ahead and draw this because we're going to need that anyway. So here's my cone-shaped container. And I suppose sand is pouring in out of some kind of a hopper. Okay, so it's falling into my container, and I'm going to say my container is about at that height, full of sand at this point. Now, before we move on, I want to think about and talk about this amount that we've been given here. What is it? So there's a few little details that are going to tip us off in exactly what this is. First of all, it's centimeters cubed, so that's talking about a volume. And second of all, it's per second, so that means it's a rate. It also obviously says it's a rate right there. So this is a rate, and it's a volume, and it's volume per time. So this is dV by dt, which is the change in volume over time, and it's positive 2, and it can be useful to write out the units in some cases. It's a good habit, and it's important to know that it's positive, because the volume could be negative. If the sand is pouring out of the cone, then it would be a negative volume. The volume would be decreasing, but the volume of this cone is increasing because it's pouring into the cone, so it's positive. So thinking about whether it's positive or negative is super important. The container, now this is the overall container, has a height of 8 centimeters. Okay. And a diameter of 6, so that's all the way across here, and that's going to be 6 from here to here. So diameter of 6, and I always like to, and this is in centimeters, I always like to write out the radius too, realizing that I may need the radius, and it's obviously easy math to do, but just some people forget that you might actually be talking about radius and just use the number you're given. So I like to write them out, so I've already thought about both. Find the rate at which the height. So this is one of the tips. What are you solving for? So we are supposed to be finding the rate at which the height of the sand is changing. So that's dH by dt when the height of the sand is 6. So at h equals 6. So this h is different from this h. This h, which is 8, is the overall height of the entire cone, but this 6 is this height. It's the height of the sand. Okay. So I think I've listed my givens. I know what I'm looking for. I kind of know what I have. Now I'm going to write out the formula that I'm going to use, and I'm talking about volume of a cone, so I'm writing out the formula for volume of a cone. 1/3 pi r squared h. And if you didn't know what to do and you were stuck, I think what you would have to do, should still be able to get this done. You should be able to draw the diagram. You should be able to think about your givens. What are you finding? Which ones are rates? Which ones are knots? All of that is stuff you should be able to do, even if you're not exactly sure how to solve the problem overall. And then you might get to this step and you might say, well, now I'm stuck and I don't know what to do next. All I can say is you would have to look at your formula and say, when I take the derivative, this h will in some way at least turn into the dh by dt that I'm trying to find. So that's a good start. I've got a formula that when I take the derivative, it will have the thing I'm trying to find in it. It'll have dv by dt over here, which I'm given, so that's also a good thing. That makes sense. But it's got this r, and when I take the derivative of this is actually product rule. The radius is changing as well, so I can't sub in for radius. Anything that's changing, you can't sub in until after you've taken the derivative. So I can't sub in for r, I can't sub in for h until after I've taken the derivative. And that means that since both of these are changing, this would actually be product rule. And that would be a disaster, partly because it's a more complicated derivative, but also because I don't know anything about r. I could find what the radius is, but in particular, I don't know anything about the rate of the radius. I don't know dr by dt, and I'm not looking for dr by dt. So if I took the derivative of this right now, I would get a dr by dt and a dh by dt and product rule, and I wouldn't be able to continue to solve. It's possible, I think, actually, but it's more complicated. So the easiest thing to do, and this is where the total height of the container and diameter of the container that you're given is actually useful information. This is where it comes into play. So what it means, the first thing you have to realize is if the overall total height of the height of the cone is 8 and the diameter is 6, no matter what height you're at, so even if you're at this height of sand, which is what we're worried about, which is 6 centimeters, it will be in the same ratio of height to radius. So that's what we have to know, which means radius over height, no matter how full of sand it is, will always be 3 over 8. So remember, I'm using radius, which was 3, not the diameter 6, because that's what my equation has, radius, so that's what I want to use. So now what I can do with this ratio that I've come up with of radius to height is I can actually solve it for the radius, and it turns out this is a substitution question, and I want to do the substitution before I take the derivative. You always do the substitution before you take the derivative. Okay, and 1/3 pi, this is where I sub r in, and it's squared, so whoops, I've got to do the whole thing like this, squared, and then times h. So whoops, this isn't supposed to be r. There we go. So now I've got everything written in terms of h and v. Whoops. So there's my r. This is what r was, and this was h, but now it's all in terms of h. I no longer have an r, and I can simplify this, and then I can take its derivative, and I don't have to worry about r. And this is key to solving this problem. Coming up with the ratio and subbing it in before you take the derivative. Okay, so I'm going to do a little bit of simplifying here. So 3/8 all squared is 9 over 64. You square the top and the bottom, and then I get h squared times another h. Okay, so 9 divided by 3 is 3, so I'm actually going to get 3 pi over 64 times h cubed. Okay, and now I've got a fairly simplified expression here that's got v, which will turn into dv by dt, but that's good because I've got dv by dt. And the right side, the h will turn into dh by dt, but that's the only thing I'll get, and that's what I'm looking for. I'm trying to find dh by dt. So that's all going to work. It's going to be perfect. So now we can go ahead and take the derivative. So derivative of v with respect to t is dv by dt equals, so I take this 3 and I multiply it over here. It's going to be 9 pi by 64 h squared. So it would be 3h squared, but I just took that 3 and put it in with the 9 right away. And then don't forget dh by dt. If you took the derivative and you didn't have that, you'd hopefully realize that you've done something wrong because you're solving for dh by dt, and if you don't have it in your formula, then there's something wrong. Now that I've taken the derivative, I can sub in. So if we go back up, we're finding dh by dt when h is 6. So I can sub that in. 9 pi over 64 times 6 squared dh by dt. And you know what? I got to go back because I can sub in for dv by dt as well. It's 2, positive 2. So I might as well put that in also. Now I can do 9 times 36, which is 6 squared, obviously. And that's 324 over 64. And if you can do all of that kind of at once and simplify, that's a good thing to do. So I get 2, and I got 81 over 16. So 81 pi over 16 dh by dt. And then bringing the 81 pi over 16 to the other side by dividing. The 16 goes to the top, so I get 32 over 81 pi equals dh by dt. It wanted an exact answer, and look at that, we're done. Okay, so then this is the rate of change of the height, so we would say therefore the height of the sand is increasing. You don't say is positive 30, or you don't just say what it is. You have to say, you have to interpret what that actually means. So the height is increasing by 32 over 81 pi, whatever value that is, meters. Whoa, was it meters or centimeters? And it was per second, so centimeters per second. Okay, so include units, include your value, and state whether it's increasing or decreasing, or it's moving away from something or towards something, however you say it. Okay, so just to recap a little bit, we did our diagram where we did some thinking about different values, thinking about the ratio. We wrote out our givens and came up with our ratio for the substitution. We did the substitution before taking the derivative, simplified a little bit, got our simplified form so that we could then take the derivative, subbed in the rest, and solved for what we had to. Okay, let's take a look at one more. A lighthouse is 400 meters across from a straight shoreline. The lighthouse is revolving at 2 revolutions per minute. Find the speed at which the light is moving along the shoreline at the moment when the light is 1,200 meters away from the closest point between the lighthouse and the shore. Found your answer. Round your answer to the nearest meter per minute. So again, we're going to go ahead and draw this. I'm going to draw the shoreline here. And I'm going to draw a lighthouse out here. And it says it's 400 meters apart. So that's good, always at a right angle. So there's my 400 meters from there to there. Now there's 1,200 meters where the light is actually shining. So this point, which I will call X, equals 1,200 meters. But that's changing. This is not changing. So we don't have to worry about it. This is changing. Again, you always want to think about what is changing and what is not changing. If it's not changing, you can sub in whenever you want, as soon as you're ready. If it is changing, you can't sub in until after you've taken the derivative. Last thing I'm going to label here is theta, and then we can start writing out some of our givens and that sort of thing. So 2 revolutions per minute, let's think about that. That was the first one that came. So 2 revolutions per minute. Well, 1 revolution is, if it's a circle, starting here, that's all the way around once. So what is that measurement? That's 2 pi. So twice around is going to be 4 pi. So therefore, the revolutions per minute, which is the rate of change of the angle, is 4 pi per minute. Radians per minute. Okay? So d theta by dt. Now it says, where is it? Find the speed at which the light is moving. So we are finding, what is that? That is the rate of change of x. That's the rate of change of the light moving along this point here. So find dx by dt, and we've already stated this, but when x equals 1200. So now I'm gonna take a pause here, and I'm gonna go over and I'm gonna write my formula. I always want to use one thing that's not changing, and then the thing that's changing that I'm trying to actually solve for. So I'm going to use the 400 and the x, and how are they related? Well, they are related to each other by tan. Tan theta is opposite over adjacent. So tan of theta is opposite, which is x, not 1200. You can't sub that in yet. So x over 400. Okay. Now I can go ahead and take the derivative, because I'm not doing any substitution or anything here, so I can take the derivative. If you remember, the derivative of tan is secant squared. And you got to do your d theta by dt. And this is like, the derivative of 2x is 2, so the derivative of 1 over 400x is 1 over 400. But then don't forget the dx by dt. And some people think this is like a quotient rule, and they start doing weird stuff. But it's just like 1 over 400x. So the derivative is just 1 over 400. But since it's with respect to t, I got to do the dx by dt as well. Now, this is good. We're almost there, except there's one problem. We don't know what theta is, and you could find theta, but the way we generally do it is we come up with an expression for secant theta instead, or we come up with the exact value, not really expression, for secant theta instead of coming up with theta. That way we can do an exact answer. So secant is the the reciprocal of cosine, and cosine, so now I'm coming off to the side over here. Cosine of theta is adjacent over hypotenuse. So that means secant of theta is hypotenuse over adjacent. Well, do we have adjacent to theta? We sure do. It's 400. Do we have the hypotenuse? We don't. So now we have to go ahead and find the hypotenuse. And how are we going to do that? We're going to do that with Pythagorean theorem. So the hypotenuse at this time, when x is 1200, h will equal the square root of 400 squared plus 1200 squared. And that works out to 1.6 million. Okay. So now I can take this and I can sub it in, and it's 1,600,000 over adjacent, which was 400. Now, however you choose to simplify this is up to you. I like doing it like this. I'm going to actually take this 400 and bring it in to the square root sign. So this ends up being 1,600,000, 1.6 million over 400 squared. So if I bring it into the square root sign, I have to square it, because then it equals the same thing. And when I do this on my calculator, 1.6 million divided by 400 squared, guess what I get? I get 10 So this works out to the square root of 10. And that is worthwhile doing a little bit of simplifying because that's a much easier thing to deal with than these big numbers. It would all work out the same, but it's worthwhile doing a bit of simplifying. The other thing you could do is if you could simplify this by finding a perfect square that's in there, but it's a pretty big number, so bringing the 400 in and then squaring it and just doing the division on my calculator was easiest, gave me the 10. Now I can go ahead and start subbing in all the things that I know. So secant squared, I'm actually going to just give you a quick reminder that that means this. So secant theta is root 10, so this is root 10 squared. D theta by dt is 4 pi equals 1 over 400 dx by dt. And we're looking for dx by dt. So bring the 400 over. I get 400 times 10, which is 4,000, times 4 is 16,000 pi equals dx by dt. Now this one actually doesn't say exact. It says round your answer to the nearest meter per minute. So when I multiply 16,000 by pi, I got dx by dt is approximately 50,265 meters per minute. That is more than 50 kilometers. Now that's not per second, but that's per minute. That is still pretty fast. And if you remember, we did talk about this, not that it really matters, but when the light is getting further away from the closest point is when it's moving its fastest. So the fact that it's 1,200 meters away, it's moving very, very fast. So that all makes sense. Therefore, we don't worry about whether it's moving away or towards. The question may indicate something like that, and in that case you might be able to, but generally speaking we don't know and we don't really care in this case. Usually we care if it's increasing or decreasing. In this case we don't. Therefore the light is moving at 50,265 meters per minute. That is fast. So that is a trigonometry question. That's a really good one to cover because it does this very different stuff. It's not quite as intuitive how you deal with the secant theta, and then we have to do Pythagorean theorem and secant theta in order to be able to sub in. After I've done all of this, I come back and I do this substitution there. So we come down doing our formula, then we go over to get our values to substitute. We do all of that work. And then when we've done that work, we come back, right? And that's how we, generally speaking, do these trigonometry questions. So that's it for Unit 5. We looked at a couple of examples, or sorry, Unit 6. We looked at a couple of different examples, but there are others. You can look back for some of those other ones, but it's a quick review of some of the specifics of these types, but in general, the kinds of things that we want to do, like looking at givens, drawing diagrams, formulas, and thinking about what we're solving for, and thinking about looking ahead when you're going to take the derivative, what kinds of dx by dt, d theta by dt, dr by dt, what kinds of things are going to come out of that, making sure we don't have product rule, that kind of thing. All good things that you should be explicitly thinking about when you're solving these questions.